All right, so chapter 3 is talking about probability. So this test 2 is talking about probability for chapter 3 and probability distributions for chapter 4 that we will do next week. So just dealing with probability now. We've probably seen probability in the past. We're just going to kind of take what we know and then, of course, add to it. So starting off with some definitions, an experiment is a process that when performed results in one observation or one outcome. So for example, if you roll a dice, you're going to land on one number. So that's an experiment. That one number you land on is going to be your outcome, so a possible observation from an experiment. So again, if you roll a dice, you're going to your possible outcomes are 1, 2, 3, 4, 5, 6. The sample space is the collection of all outcomes for that experiment, and we're going to denote it. That word denote just means that we're going to like label it. We're going to call it S. An event is a collection of one or more outcomes of an experiment. So for example, we have two different types of events. We have a simple event and a compound event. A simple event is an event that includes only one of the final outcomes of an experiment. And we denote it by E, and this is like a subscript, so E sub I. So if it's event 1, it's E sub 1, event 2, E sub 2, 3, 4, 5, so on and so forth. Versus a compound event is an event that includes two or more of the final outcomes, and we label it, we denote it by the letter A, capital A. Probability is numerical measurement of the likelihood of a specific event will occur. We label it P of X, kind of like function notation F of X. So this would be the probability of X happening. Let me write that down. Probability of X happening. Or X occurring. So for probabilities, it's numerical measure. We use decimals to label it. So we have two properties. The first property says the probability of an event always lies in the range 0 to 1, meaning it's either not going to happen, so 0, or it's for sure going to happen, which is 100, or 1 in this case. So we can label that mathematically as our probability of an event, so E sub I, is in between 0 and 1, less than or equal to, 0 is less than or equal to the probability is less than or equal to 1, meaning that the probability lies somewhere between 0 and 1. Notice there's no negatives, nothing bigger than 1. It could be 0, which means it does not happen, all the way to 1, which means it's for sure going to happen. So any decimal within there. Obviously, the lower the number, the less likely it's going to happen. The higher number, the more likely it's going to happen. So that's our first property. Our second property is if we add up all the probabilities, the sum of the probabilities is always 1. So for example, if I were to flip a coin, you get heads or tails, right? Probability of heads is 1 out of 2, 1/2, so 0.5. Probability of tails is also 1 out of 2, 0.5. So 0.5 plus 0.5 will add together to give us 1. We're going to use that to make sure that we have all the probabilities together. We can say that using our symbols from previous chapters. Remember, we have sigma, which means the sum of our probabilities of an event, so P of E sub I, which is the same thing of probability of event 1, plus the probability of event 2, plus the probability of event 3, plus blah, 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 and that's going to equal 1. Adding up however many events that we have is going to equal 1. So those are our two properties of probability. So I try to kind of break it up and say, okay, here's some definitions. Based off these definitions, let's do an example. Remember, these examples are, there's the notes right there for you. These examples are straight from your homework, quizzes, tests, all that type of thing. So make sure whenever you're doing the homework, all the assignments, you have these next to it so it should look exactly the same and kind of mirror off. So, yeah, question?
What was the I for?
Oh, the I right here?
Right.
That's just kind of like in general. So it's generalizing however many events that you have. So for example, we talked about rolling a dice. So what's the probability of landing on a 1? What's the probability of landing on 2, 3, 4, 5, 6? So we'd have 6 things. So it's just kind of generalizing it to say however many events could occur. Just kind of like For example, like on an ordered pair, we call it x, y, and x just counts for every single point on that line. Same thing, it just is generalizing it. Thank you for asking a question. Other questions while we're here? All right, so the first example says, which of the following values cannot be a probability of an event? So we're going to select all that apply. So which ones cannot? So notice the words cannot.
1.2.
1.2, good, why?
Because it's over 1.
Good, because it's over 1. What about 0.97?
That could occur.
That's fine. What about 1? That's okay. 1/4? That's okay, it's a fraction. Negative 1/2.
No.
Nope, we can't have a negative. Let me write here, it's over 1. Here we cannot have a negative. Eight over 7. 8 over 7, let's see. Oops. 8 divided by 7. 1.14. No.
I was scared there, I'm not gonna lie.
Don't be scared.
I just saw it was fractions.
Yeah. So think about it. Oh, it's over 1. So we can't have it. Negative 0.3. Nope, we can't have a negative. And 0.
Yes.
Yeah, we could have 0. As long as it's any number between 0 and 1, including 0 and 1. So this one cannot be a negative. So let's write a little note just for our note's sake. Can be any number between 0 and 1, including 0 and 1. So that way it makes sense now, but whenever you go back and look at your notes, you can kind of remember why we talked about that stuff. So before we go on to the next example, how could I help you with this first example? Next one, choose the correct sample space S. Remember, the sample space up here is a collection of all outcomes for an experiment. For the random experiment that's described, a pair of dice is rolled and the number of dots on the two faces that come up is recorded. So what are our options if we take two dice, right? Die is 1 or 2?
Die is 1.
Okay, sorry, brain part again. All right, so 2 dice, right?
No.
Whatever. Okay, 2 things. You know what I'm talking about. 2 of those cube things. And we roll it. So what are our different options? Okay. Could I get 1?
No.
No, why not?
Because no matter what, it's always going to roll to a number higher than 1 because you have 2 of them.
Right, so if we have 2 dice, the lowest number is going to be 1. If we have the lowest number is 1 on the first die, whatever, cube. Second one is 1. The lowest number we could get is 2. So this one cannot be an option, and this one cannot be an option because 1 is not an option for an outcome. We take 2 dice, whatever, 2 dice. I'm going to say it. I don't care if it's grammatically correct. 2 dice, and we roll it. The lowest number we're going to get 2. Can we get 3?
Yes.
Yeah, I could get 2 on one and 1 on the other. 4, 5, 6, 7, 8, 9, 10, 11, 12, because 12 is the highest number because our highest number is 6. So 6 on the first one, 6 on the second one. Our highest number is going to be 6. So boom. This one doesn't because that doesn't have 3. So here is our answer. Here's all of our different possible outcomes. And that's what makes S, which is our sample space. You feeling good so far? Yeah, I feel like we're only on the second example, but yeah. All right, so keep rolling with this whole probability thing. There's 3 different approaches to probability. Classical probability, which is all simple events are equally likely, and that's kind of like our normal thing. So for a simple event, we said for simple events, there's only one outcome. So that one outcome out of the total number of outcomes there are. versus a compound event we said could have multiple outcomes, so the number of favorable outcomes over the total number of outcomes. So for example, if we flip a coin, right, you're only going to get heads or tails, so they're equally likely. So it's going to be a simple event. You're only going to get one thing out of two, so either way they're both 1/2, whether you get probability of heads or tails, versus let's say the probability of rolling the dice and getting an even number, right? So there's different, you can get 2, you can get 4, you can get 6. So there's 3 different even numbers, so 3 is our favorable outcomes out of our total 6 options. So that's kind of like what these two things mean. So let's keep rolling. These are just formulas, which by the way are on our formula sheet, which is on the last page. Here's your chapter 3 and chapter 4 formulas this page will be given to you on test 2. So just kind of keep this in mind, have this next to you whenever you're doing your homework, your quiz, your review, so that way you're used to using these formulas. Don't memorize anything besides definitions. All right, so that's classical probability. The next one's relative frequency, which is the probability of A is F over N. So F is the frequency. That event A occurs, the number of times event A occurs, all over N, which is the number of times the experiment is repeated. Is done. So the frequency that A occurs all over the number of times it's done. This is relative frequency. It's also called empirical probability. That's just another word for it, empirical probability. Relative frequency probability or empirical probability. That word empirical means experimental. So you're actually performing an experiment, and based off the experiment, what's your probability? So going back to the heads and tails example. So our classical probability would say you have 50% chance of getting heads, 50% chance of getting tails. In theory, that's what should happen. That's our classical. If I were to sit here and actually flip a coin, let's say like 10 times, and let's say out of the 10 times, I get heads 3 times. So my relative frequency probability would be 3 out of my total 10. It's supposed to be 50-50, but it wasn't. So this would be based off my experiment, what were my results? This is relative frequency or empirical probability. So last one is subjective probability. The probability that's assigned to an event based off subjective judgments, beliefs, or hunches. So no data is involved, no math. So no numbers or data. All right, so based off these, here's 3 examples, and let's label these, which type of probability is each. So let me take off this no numbers, and I'll explain why in 1 second. It makes sense in my head, but I want that to confuse you. All right, so a coin was flipped 31 times and tails was observed. Tails happened 11 times. So, why are you laughing at me? Oh, okay. So they actually performed an experiment. So they actually flipped the coin 31 times and watched tails occur 11 of those times. So this was actually an experiment. So it's going to be relative frequency. I'm going to put a little side note, an experiment was performed. And then what is the probability? So find the probability now. So the probability of landing on tails, so the probability of T, would be our frequency. So how many times did it land on tails? 11. Out of how many times was it flipped total? 31. So 11 over 31, let's put this into our calculator. And we get 0.35. So that is the first one. Second one, what is the probability of drawing an ace out of a standard deck of cards? So, in theory, what's the probability? So if this is just in theory, we're not going to actually perform the experiment. This is going to be classical probability. It's like in theory, we didn't perform the experiment. We're just saying what should our probability be. All right, of drawing out an ace. So probability of getting an ace. How many aces are in a total deck of cards?
4.
4 out of how many cards are there total? 52. Bingo. So 4 aces out of 52 total. So 4 out of 52, that would give us 0.088. Sure. All right, so we did relative, we did classical, so the last one's probably subjective, but let's read it. There's a 30% chance that I'm going to skip class tomorrow because I'm really tired. For one, a lame excuse. For two, I'm just kidding. So do you see, like, there is numbers, so that's why I erased that, but, like, there's no data, there's no math behind getting that 30%. That was just like a hunch, you know, like throwing out a number. So based off that hunch, this is going to be subjective probability. I want to know someone who's not always really tired. I feel like I live in a state of always being tired. All right. Okay, now what is our probability? So the probability of being a slacker. No, I'm just kidding. So probability of skipping is, they told us 30%, but putting this in decimal form. So moving our decimal 2 times to the left. So 0.30 or 0.3. That's fine too. So those are 3 different types of probabilities and examples of each. So we can kind of differentiate between the 3. So questions, comments, concerns. How could I help you with this one? All right, so let's do another example. It says use the spinner below to calculate the following probabilities. Round our solutions to 2 decimal places if necessary. So that means 2 numbers after the decimal point. So what's the probability of getting an 11 or 2? So looking here, I have 1, 2, and 1, 11. So I have 2 options to get on 11 or 2. Out of how many options total? 12. So 2 options out of our 12 total. So 2 out of 12 in our calculator, 0.1666. Said round at 2 decimal places, so we're going to round this first 6. Looking next door is a 7. Remember, 5 or higher, it's going to round up. So it's going to be 0.17. So notice that word or meant that we added the different options. I had 111 plus 12. Keep that in mind. We're going to use that in the future. So I had 2 options out of our total 12. All right, next one. What's the probability that an odd number is obtained? So let's look at our odd numbers. I have 1, 3, 5, 7, 9, and 11. So I have 1, 2, 3, 4, 5, 6 odd numbers. Out of, we said we had 12 numbers total. So 6 out of our 12, without even using our calculator, 0.5. Done. All right, last but not least, what is the probability of landing on a multiple of 4? So what's our multiple of 4s here? So I have 4, 8, 12. So I have 3 options that are multiples of 4 out of our 12 options total. So 3 out of 12 will give us 0.25. Done. So those are the ways that we calculated these probabilities. And these are examples of what type of probability. So notice we're looking and kind of like doing the math, so we know it's not subjective. There was no experiment involved. We're just looking about, in theory, what's the theory that it should land on it. So we know that's going to be classical. Classical. Great. Questions on these before we go on to the next one? All right, so next we have another definition, the law of large numbers, which says if an experiment is repeated over and over and over again, as much of the times that it's like approaching infinity, so just like constantly over and over again, the probability event from the relative frequency approaches the actual theoretical probability. So it's saying the more times you do an experiment, which kind of makes sense, but the more times that you do an experiment, the closer that the relative frequency, which is experimental, will get to the actual theoretical probability. So let's go back to like the flipping the coin example. We said in theory, classically, I don't know if classically is a word, but classical probability would be 50-50, right? 50 heads, 50 tails. So if I did an experiment and did relative frequency probability, if I did it 5 times, and let's say out of the 5, like 2 of them landed on heads, right? Or let's say out of 10 to make it easier. Let's say out of 10, 2 of them landed on heads. So 2 out of 10 is 0.2. That's not very close to 0.5. But if I did 100 times, I would get close to that 0.5. If I did it 1,000 times, which I don't want to, but if I did do it 1,000 times, it'd be closer to 0.5. And then if you keep going, getting more and more and more, the closer that experimental relative frequency probability would reach the 0.5. That kind of makes sense though, right? Like the more, it's kind of like, what's that old thing, like practice makes perfect. The more times you do it, the better, the more perfect it's going to be. That's all that's saying. So now we have the union of events. Mathematicians, I used to say are lazy, but we're just efficient. So instead of saying the union of events, that's kind of like a weird thing. We say it's A or B. And we're going to use the symbol for or. It's like an uppercase U. It's like a union symbol. And some of you who've seen college algebra have seen this before. We united 2 like interval notations together. So it's not a letter, it's a symbol uniting 2 sets together. So A is a set and B is a set. All right. So the union of events is, we call it or. So it's going to be, I like it because it's like that letter U for union. Looks like the U for the symbol. So that's how I keep them apart. Is the collection of all outcomes that belong to either A or B. So if A is 1, 2, 3, 4, 5, and B is 4, 5, 6, 7, 8, we need to find A or B. So find A union B. So that squiggly bracket just means it's set. It's kind of just like grouping our numbers, our answers together. Again, if you took college algebra, we've seen that where we set notation. And so if it's an A or B, so it's like we're putting these 2 things together, A or B. So 1's an A, 2, 3, 4, 5. Or B, 4 is already here, so I don't have to write it twice. 5 is already here, so I don't have to write it twice. So 6, 7, 8. So, oh, that was terrible. I'm not good at like my back half of my bracket. So just putting all these numbers together. So 1, 2, 3, 4, 5, 6, 7, 8 are either in A or they're in B. They're in one of these sets. So a little note here. Don't great duplicates. Duplicates. So meaning like 4 was twice, like in both of them. So don't write 4 twice, it's just 4 one time. So that's the union. A lot of times people we're going to talk about Venn diagrams in a second, and Venn diagrams are just a very good visual way of organizing our data. And if you think about a Venn diagram, if let's say this first thing is A, my circles aren't very good, and the second circle is B, our union would be everything together. We're talking about everything that's in A or B. Versus the intersection, then we have and AB. So and is going to be the upside down union symbol. The way that I think about this, again, super weird, but it helps me, is like an N. It kind of looks like an N. I don't know. Weird, but that's helped me, so if it helps you, great. Is the collection of all items that are in common to both A and B. So whatever's in common. So going back to our little Venn diagram, it's whatever numbers are in common. So whatever is in the intersection there in the middle. Hence, intersection. So what is in A and B? What numbers? Using these same things. What is it?
4 and 5.
4 and 5. Bingo. All right, how could I help you with this so far? So the numbers that are in common. So this is kind of like the main word we're looking at. All right, let's keep rolling. Page 3. Oh man, I need to put a little space there, sorry. So I know I'm super particular, but whatever. Joint probability is the probability of A and B. So it's the probability of the intersection of the two events. So you'll see that word joint probability, and we're just finding the probability of getting A and B. The complement, which some of us have seen before in geometry, maybe a long time ago. The complement is the complement of event A is the collection of all possible experiment outcomes that are not in A. And we label it as A not, so A with a little apostrophe, or A bar. Some other books might do A sub C, with an exponent of C. But this book doesn't really do that. But just fair warning. Going back to geometry, remember we did the complement of an angle, and it was the two angles add up to 90. So whatever is not an A. So whatever, same thing. All right, so if we have the sample space S, let's do an example of a complement. So S is 1, 2, 3, 4, 5, 6. These are all of our possible outcomes. And A is 1, 2, 3, 4. So what is the complement of A? And then we're going to find the probability of both. So the complement of A, we can say A not, A complement. So it's A and an apostrophe. It's a power of 1. All right, so what's not an A from our sample space? 5 and 6. All right, marginal probability is the probability of a single event without the consideration of any other events. So it's also called a simple probability. So versus a conditional probability is the probability that an event will occur given that another event has already occurred. And we label it, we denote it as probability of A, and with this big vertical bar, B. But we say the probability of A given B. The probability of A given that B has already occurred. So for this, we have what's called Bayes' theorem, which is on our formula sheet. And it's the probability of A given B is the probability of A and B. So this is our joint probability all over the probability of B. Here's the thing that I noticed. See how this kind of looks like a fraction? Again, a weird thing, helps me. But see how B is like kind of in the bottom of our fraction? So it's in the bottom of our fraction here. So, looks big, bad, and scary. Let's do one together. So, again, this is on your formula sheet too. So if you ever forget it. Let's do an example of this stuff. So the probability that a randomly selected IRSC student is an athlete is 0.16. So they tell us that. The probability that a randomly selected IRSC student is a biology major is 0.14. And the probability that a randomly selected IRSC student is a biology major and an athlete, so notice that word "and" there, is 0.13. Calculate the following probabilities, round to 3 decimal places. All right, so all right, so let's write kind of like what they gave us. So the probability that they're an athlete, I'm just going to label it as A. So A for athlete is 0.16. And they tell us the probability that the person's a biology major, so I'm going to use B, is 0.14. And the probability that they're both a biology major and an athlete, so B and A, which is the same thing as saying A and B. It doesn't matter the order because it's whatever they have in common. And they tell us that's 0.13. So that's what they give us. So the first one says, determine the probability that a randomly selected IRSC student is a biology major given that its student's an athlete. So the probability of biology majors, so B, given, which is our vertical bar, A. Notice order does matter because it matters what's the bottom of our fraction. So B given A, biology major given athlete. So using our formula up here, probability of B comes first. So B and A all over the probability of A. Notice my bottom's A, so the bottom's A. So just plugging in our numbers, probability that they're both is 0.13 over the probability that they're an athlete is 0.16. Plug this into my calculator and we get 0.125, 8125. It said round to 3 decimal places, so rounding this 2, looking next door is a 5. So it's going to round up, so 0.813. So they give you everything that you need. It's just a matter of reading it, really, just reading and knowing what to put where. Let's do another one. The probability that a randomly selected IRSC student is an athlete, so A, given, so a vertical bar, biology major. So this one's the same thing but opposite. So athlete, given, biology major. So probability of A given B. So same thing, it doesn't matter the order of the top. So probability of them both, so A and B, all over the probability of the bottom, which is B. So what's the probability that they're both? 0.13. What's the probability that they're a biology major? 0.14. Putting this into our calculator and we're done. 0.13 divided by 0.14 is 0.92. We're going to round this 8. Looking next door is a 5. So it's going to round up to 6.
9?
I don't know. Yeah. 9.
Yeah,
I wrote 9 and then I'm like, but I said, I don't know.
You said 6.
Sorry. That's why I was like, yeah, I don't know. 0.929. This 8 looking next door is a 5, so that 8 is going to round up to a 9. My bad. So this is conditional probability. We're going to do more examples of this. Don't worry. But questions so far? Questions so far? this is, again, just reading and knowing what the symbols mean. It's kind of like, what is that thing that's like you're decoding? Like, like in elementary school, you know how like you had like symbols and then you had to make the symbols and you made like a little, no, you guys are, yeah. Like there's symbols and you're like said, okay, like the smiley face is a letter A or like the dot is a letter B. And you have to see what the symbol is. Yeah, it's kind of like decoding that. It's kind of like all we're doing. All right, so independent versus dependent. So independent events are two events that are independent, duh. If the occurrence of one event does not affect or does not change the probability of the occurrence of the other. So the way that we show if it affects it or not is this formula. Probability of A given B is equal to the probability of just A. It doesn't matter if B occurs or not, it's still going to stay the same. Versus a dependent event, oops, don't tell anyone I wrote on the wall. Dependent events are two events are dependent if the occurrence of one event does not change. Pedro, does not change or affect the don't tell. I erased it. No one knows.
You just recorded it.
Oh. Oh well. No one's gonna know. I didn't mean to. At least I didn't put a hole in the wall. All right. Two events are dependent if the occurrence of one does change or affect the probability of the other. So to show that if we have the probability of A given B, it's not the same as probability of A because given B is gonna change it up. Because of this, we talked about this before, so I just kind of want to bring this back up. Sampling with replacement versus sampling without replacement. Sampling with replacement means that if you select a random number, you're going to return it before you select another one. So for example, if you grab like a ball out of a bag or something, and it's like there's, like that infamous example that it's like, okay, there's 2 red balls, 3 yellow balls in a bag, right? Or marbles or whatever, and you take one out. So with replacement means that you're going to replace it. You're going to put it back before you select the other one. Versus without replacement says that you're not going to return it. So you're going to take it out and you're going to keep it and select it again. So with replacement means you're going to put it back before taking the next one. Without replacement means that you're going to take it out and leave it out. Note, always assume that 2 or more events are dependent unless it's otherwise stated. So we always assume they're dependent unless we can prove otherwise. Next page. Let's do an example. An experiment consists of randomly selected single digits from 0 to 9, where each digit is equally likely to be selected. And it gives us different events, A, B, C, and D. And it says which 2 events are independent. Remember, or recall for this example that 0 is considered even.
Is or isn't?
It is. So is an even number. So sometimes it's even, sometimes it's like nothing. So for this example, they consider 0 to be even. All right. So we have to say, is B and C independent, A and D, A and B, blah, blah, blah. So we need to test each one of these. So going back to that thing, are they independent or not? So does it satisfy this condition? A given B is the same thing as probability of A. So probability of A given B, is that equal to the probability of A? And we have to do that for each one of these. So let's start off with B and C. B and C. It doesn't matter what order, because it should give you the same answer either way. So let's do the probability of B given C is the same thing as the probability of C. We're seeing if these 2 things are equal. All right, so what is the probability of B given C? All right. So going back, we're going to do this 2 ways. The first way is the way using the formula. Probability of A and B all over the probability of just B. So probability of B and C all over just the probability of C. So we have 9 from 0 to 9. So that means there's 10 options. Be careful with that. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is 10 options. So B is a number greater than 3. So let's write all these out, starting off with A. So an even number. So 0, 2, 4, 6, and 8. Number greater than 3. So 4, 5, 6, 7, 8, 9. A number less than 7. So 0, 1, 2, 3, 4, 5, 6. And then 1 or 7 is just 1 or 7. So.
And we don't include 7 for C?
No, just less than. Just less than. If it said less than or equals 2, then we would include 7. Great question. All right. So B and C. So how many things are in B and C? So 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But these numbers are already counted here. So it's going to be everything. So 10 out of 10, which is 1, over the probability of C. So we have 1, 2, 3, 4, 5, 6, 7 things out of 10 total. So 1 divided by 7/10. Notice my 7/10 is in parentheses, so that way I can separate it from the top. And we get I messed up something, but I don't know what I messed up. Probability of B and C. Is that the same thing as probability of B for 1? One, 2, 3, 4, 5, 6, 7. 9, 10. Oh, I know what I messed up. My bad. Sorry. I was getting scared for a second. All right, so B and C is stuff that they have in common. I was thinking or here. B is whatever they have in common. So how many things do they have in common? Whew, I was like sweating because I couldn't figure out what was wrong. Got it, sorry. So what do they have in common?
4, 5, and 6.
4, 5, and 6. So 3 out of our 10 total. And then C has 7 things out of our 10 total. So 3 out of our 10 things total divided by 7 out of our 10 things total. Oops. Notice, make sure to put this top fraction parentheses to separate it from the whole fraction. And we get 0.429, let's say. Now, is this the same thing as the probability of B? So just looking at B, I have 1, 2, 3, 4, 5, 6 things out of our 10 total. So 6 out of our 10 total is 0.6. Not the same, not equal. So A and B are, I'm sorry, B and C are not independent. So my problem was I said and. Okay, let's do this easier, right? So here's the second way. All right, so when we have something like this, when we're looking for B given C, we're only looking, so whenever it says given C, it's saying that you're only looking at C's. So out of our C options, how could B occur? So only looking out of our C options, out of 0, 1, 2, 3, 4, 5, 6, which numbers of these are greater than 3? 1, 2, 3. 3 of them. And this would be 3 out of our 7 total. Well, only looking at C. So now we're only looking at C. So now our total is C. So B given C is looking at C as our total. So there's 7 things on the bottom. And then looking at our C's, which one of these is greater than 3, which is our B option? 3. So 3 out of 7, which 3 out of our 7 is going to be the same thing. Let's do another example. So let's do A and D. A and D. All right, let's just try to look at it like easier. So probability of A given D, is that the same thing as the probability of A? So A given D means that we're only looking out of D. So we're only looking at 1 and 7. So those are 2 options. So the bottom is our D. Just like the bottom here, the bottom is our D. We have 2 options in D. Out of these 2 options, which ones satisfy A? Which one of these is even? Neither. So 0. 0 of them are even. So 0 divided by 2 is 0. Is this equal to the probability of just A? Probability of just A is 1, 2, 3, 4, 5 out of our 10 things total. So 0.5. 5 out of our 10 things total is 0.5. Not equal. So A and D are not independent. They're dependent.
So the first one you use the formula, and then the second
Right.
one you're using
The shortcut.
The shortcut way.
Yeah. So this is using the formula way, just so you can kind of see whatever way you like better. This is the formula way. B and C we did using the formula that we did on the previous page. But this formula made
That
sense.
makes it tricky, because you want to look at it as and, like you were saying.
Right. So instead of having to use this formula, it's this. You still get the same thing, because what happens here algebraically is our 10s cancel, and you still get 3 out of 7. So this is just looking at it like a shorter way, a shortcut. So it's just saying it's the same exact formula, just 2 different ways of thinking about the same formula. So this is saying out of our D option, so if we're saying given D, it's saying that they have to be in D. So it has to be 1 or 7. We have 2 options. Which one of these could A occur? A is even. So out of our 2 options, how many are even? 0. So we're still doing A given D, whether you do the formula or whether you do the shortcut. Same answer. Let's do one more. A and B.
We always take the first.
It doesn't matter the order. You'll get the same answer. Because you could flop these around and you'll get this. You'll get either way that they're not equal. So the probability of A given B, is that the same thing as just the probability of B? All right, so using our shortcut, B is like given B. So those are the things that we're looking for. We're only looking at B. So we're only looking at 4, 5, 6, 7, 8, 9. So we're only looking at 1, 2, 3, 6 options. Out of these 6 options, which ones satisfy A? A is even. So out of 4, 5, 6, 7, 8, 9, how many are even? 1, 2, 3. So 3 out of 6 is going to be 1/2, so 0.5. And is that the same as B? So B is looking at numbers greater than 3. So 4, 5, 6, 7, 8, 9. So that's 6. 1, 2, 3, 4, 5, 6 options.
Don't you want the A?
Yes, thank you. Dang, that I'm like off
I was
my
like,
game
wait a
here.
second.
Probability of A. So only looking at A. I'm sorry. I'm gonna get back on my game here. Only looking at A, we have 1, 2, 3, 4, 5 options out of our 10 total. 5 out of 10 is 0.5. They are the same, so these two are independent. Our answer is B.
The second way was much easier.
Mm-hmm.
The first way I was like,
That's too much.
Yeah, it's too much, and I didn't want to just jump here because we talked about doing it this way, so I kind of wanted to relate it. And I got thrown off once I got thrown off. Focus. We'll get back. All right, but we figured it out. So now that we see it, we're going to do plenty more examples, so don't worry. But now that we see it, questions for me. And remember, keep this in mind too. We're doing this together. That's exactly the same as your homework. But your homework is purposely going to have different numbers because I want you to try it together here, use this as an example, and then make sure that you understand it and try it by yourself at home. So a lot of times it's like, okay, this makes sense when we're doing it together, but you get it home and it's like, I know we did it, but now I don't get it. So I want to make sure that you get it before you get to a quiz or a test. And if you don't, email me. Did someone have a question? Ashley, did you have a question? Joy, I thought I heard someone say something. Ready for the next one? Let's just keep doing more. We don't have a choice, so of course, yeah, we're ready. In a class of 32 students, 12 of them are dual enrollment and 20 are not dual enrollment. Suppose 2 students are randomly selected from the class without replacement. So this is going back to that sampling with or without replacement. So they're selected and then they're not put back into the pile to select again. Calculate the following probabilities around our solutions to 3 decimal places as needed. So, this is sampling without replacement. All right, so here's our first student that we select, and here's the second student that we select. So the first student is dual enrollment. So how many are dual enrollment?
12.
12 out of how many total?
32.
32. So 12 out of 32. And the second student, which we're going to multiply, how many are dual enrollment? Now, notice the first one was taken out and not replaced, so how many now are dual enrollment?
11.
11, good. So there's 11 left over. How many students are left over now? Remember that first one was taken out, so how many students are left over to choose from?
31.
31, bingo. So multiplying these two together, make sure again to put it in parentheses, 12 out of 32 times 11 out of 31. The reason why we put it in parentheses is separate. Okay, this fraction is separate and this fraction is separate. Multiplying them together, boom, there's our answer. 0.133. Looking next door to that 3 is a 0, so it's going to stay. And if we were to write this in a formula, if that kind of like helps you relate it, we found the probability that it was a dual enrollment student. And then we did the probability that it was a dual enrollment student given the first was dual enrollment. So the probability that it was dual enrollment, and then times the probability that the second one is dual enrollment given the first one was dual enrollment. So same thing for the second one. What's the probability the first student is dual enrollment and the second student is not dual enrollment? So putting this kind of like in symbol form. So the probability that the first is dual enrollment times the probability the second is not dual enrollment given the first one is dual enrollment. So let's think about it, looking at the first one. First student is dual enrollment, just like up here. We have 12 dual enrollment students out of our 32 total. Times, looking at our second choice. Second one's not dual enrollment. How many are not dual enrollment? 20. Out of how many do we have left to choose from if that first student's taken out? 31, bingo. Putting this into our calculator. 12 out of 32, separate it, group it together using parentheses, times 20 out of 31, and we'll get 0.24. I have 19, so that's going to round up to 2. Boom. Done. How could I help you on this one? So you kind of have to just think about it. Let's do another one. Let's just keep rolling. In a random sample of 175 students, were asked about the vehicle they prefer, a car or a truck. The following contingency table gives a two-way classification of the responses. So this is what's called a contingency table. It's also called a two-way classification, just two options of saying this. And what this is saying is they're classified in two ways. They're either going to be male or female, and they're either going to say car or truck. So this 89 right here is saying that 89 of the 175 were male and said car. 26 of them were male and said truck. 50 of them were female that said car. And then 10 females said truck. So it's just a way of organizing our data. That's all it's doing. Instead of like having it all unorganized, we're just organizing it. So starting off, it's very good to look at look at our different options. So that way, whenever we go to our questions down here, I don't have to do any math. Like all the math will be done. So let's say how many people said car. It doesn't matter if they're boy or girl. How many people said car. So 89 males said car plus 59 females said car. So total 139 people said car. Same thing, how many said truck? 26 plus 10. So 36 said truck. So their options were car or truck. So if we add these two together, it should give us our total, 175. So let's make sure, 139 plus 36, yep, 175. So this is our total. Kind of just a good way to make sure everything's adding up properly. Now let's see how many were male. So 89 plus our 26. So just looking at our male. So 115.
Says female.
For which one? We're just looking to see how. We're just looking at this first before. Don't look at your questions yet.
Oh.
Yeah. Don't look at it yet. And how many of these students were females? So 5 plus 10 will give us 60. Again, adding it here, because they're either going to be male or female, adding it up, 115 plus 60 gives us that total, which is 175. So it's kind of like we're good all together. So now we have everything that we need. So now we don't have to like worry about adding anything up. We're ready to go. Suppose one person is randomly selected from the group. Calculate the following, round to 3 decimal places. So what's the probability of getting a female? So we already did the math. How many females were there total? It doesn't matter if they said car or truck. 60. Out of how many students total? 175. 60 out of 175. 0.34, and that 28 is going to round up to 3. Now, what's the probability of a car? So I also want to go back. Remember back here, just kind of real quick, we talked about marginal versus conditional probability. These are what's called marginal probability. Just a single event, doesn't matter about anything else. It doesn't matter if this one said car or truck, we're just looking at females. These are marginal. This one just says car. I don't care about anything else. Versus these are conditional. So these two are marginal. And then these two are conditional. All right, so car. So how many said car? 139 out of our total 175. 139 out of 175, and we get 0.794. All right, so we're going to use that little shortcut again. If we said, what's the probability of the female given that they said truck? So we're only looking at the people who said truck. So we're only looking at this column. So I don't care about anything else. I'm just looking at the trucks. Out of these truck people, how many of them are female? 10. Out of how many truck people are there total? 36. Bingo. So this is female truck. And this is all trucks. So notice that bottom was trucks. We're going to leave it truck. So 10 out of 36. 0.2777 is going to round up to 8. So you see, I don't need the formula here. It's way easier just to think about narrowing it down to only the truck options. Same thing here. Notice that these two things, even though it's female and truck, the order matters. So probability of truck given female. So now we're only looking at females. How many of them said truck? 10. Out of how many females total? 60. So 10 out of 60 will give us 0.1666. We'll round up to 7. Last but not least, are truck and female independent or dependent? Well, we have the probability of female given truck. And is that the same thing as the probability of female? No. So female given truck, we said, was 0.278. Is that the same thing as probability of female, 0.343? No, it's not the same. So they're going to be dependent. Dependent. I'm just going to write this neater because it's bothering me. I like these tables because it kind of helps organize everything so you're not looking at a whole bunch of stuff. How can I help you with this one?
I already know I'm gonna have trouble.
How did you know that to put it with P equals female of female? Like how did you put it with that?
This? Down here?
The bottom one, the last one.
Yeah. So it doesn't. You can do either order, but I knew I wanted, because I already had the probability of female, so I wanted that I wanted to use that because I already had that. So it doesn't matter. I could have used either one of these, but if I have this one, it's like, do you see how these first are the same?
Mhm.
So you could also say the probability of truck given female is the probability of the truck, which is fine. I just had to do another calculation. I was just trying to like work smarter, not harder, and kind of use what I had. So that's why I chose those. And remember, independent was that formula. Probability of A is equal to the probability of A given B. So I was trying to put it into that formula. Thank you for asking a question. Does that help?
Mhm.
What else? What other questions? You have another one of these. Not yet, I guess. But we'll do another one of these in a second. Yeah, we'll do 2 more. Let's keep rolling. And these are just practice, because this is something that I'm sure you've never done before. I never did it before this. So, before I took this class. So it's just different. And because it's different, it's supposed to be weird. And it's supposed to take practice. If you knew it, what's the point of this class? So just keep that in mind. Mutually exclusive versus mutually non-exclusive. So mutually exclusive events are events that cannot occur together. So ask yourself, can the events occur at the same time? For example, mutually exclusive means if you can get an A in the class and you get a B, they're mutually exclusive. You can't get an A in the class and get a B. You only get one letter grade. You either get an A or a B. You can't get both, right? So they're events that cannot occur together, cannot occur at the same time. Cannot occur at the same time. You cannot get an A in the class and get a B. You get one letter grade. Versus mutually non-exclusive. Again, these are events that can occur together, that can occur at the same time. So again, ask yourself, can the events happen at the same time? So, for example, if you get an A in the class and you pass, you can get an A and you can pass. Like you can do, if you get an A, you're going to pass. You can also get a B and pass the class. So those two things can happen at the same time, so they're mutually non-exclusive. So again, no, always assume that they're mutually non-exclusive unless you can prove otherwise. So let's look at an example. There are 164 physicians practicing in Port St. Lucie. Of them, 82 are female. Dang it. I checked this 3 times for spelling. Sorry. Are female, and 50 of them are dermatologists total. Of the 82 female physicians, 10 of the 82 are dermatologists. Suppose one physician from Port St. Lucie is randomly selected. Answer the following questions, rounded through decimal places if needed. All right, so same exact concept. We're kind of doing the same exact thing. We just don't have a table this time. So what's the probability of this physician being selected as female? How many females are there total?
82.
82 out of how many total physicians? 164. So 82 out of 164 should be half. Yep, so 0.5. So this is female out of total. So next I have probability of female given dermatologists. So out of the bottom, we're just looking at dermatologists. How many dermatologists are there total? 50 dermatologists total, so 50. So we're just looking at dermatologists. So out of those 50 dermatologists, how many are female?
10.
10. So we have 10 female dermatologists. So 10 out of our 50 will give us 0.2. Are female and dermatologists independent or dependent? So going back, same thing. We could use the probability of female given dermatologist. And does that equal the probability of just female? No. It's because we had, this was 0.2, and that does not equal 0.5 because we already found those up here. So they do not equal. So these two are dependent events. Now, are they mutually exclusive or mutually non-exclusive? So let's go back. Could they happen at the same time?
Yes.
Yeah, they could. A female could be a dermatologist. Dermatologist could be a female. Doesn't matter what order. So because they can happen at the same time, so can happen at the same time. So that means they're going to be mutually non-exclusive. Honestly, the biggest thing for me, probably for this whole chapter, is keeping that definition straight. Mutually exclusive versus mutually non-exclusive. Just being honest with you. That's probably, in my opinion, the hardest part of this whole chapter.
So far,
For me.
it's been independent, dependent for me.
But thankfully for independent and dependent, we have the formula, and that formula is on our formula sheet. Where'd it go?
True.
Right here. So that kind of helps. So don't worry about memorizing that one. All right, so questions on this one. Is it getting better? The more that we do together, is it getting better? We have plenty more to do, so don't worry. But all right, so let's move into two basic rules of probability. We talked about and or, but we didn't really do that much, so let's do some more. So the multiplication rule for and probabilities, the probability of A and B. Remember we used that symbol, A and B, is the probability of A times the probability of B given A. But remember, if they're independent, the probability of B given A is the same thing as just the probability of B. So if they're independent, if we know they're independent, we can use a shortcut. Just the probability of A times the probability of B, because those two mean the same thing. Likewise, if I have the addition rule for or probabilities, so A or B, so probability of A or B, remember I had that symbol, is the probability of A, so whatever's in A, plus the probability of B, minus the probability of both. Reason being is if I have or, it's everything that's in A and everything that's in B combined. I know I said the word and, but it's whatever's in this one and whatever in this one, what's in everything, right? So if I have everything that's in A, let's say that 2 is in A and B. So 2 is counted here, 2 is also counted here. So it's like we double counted it. So because we double counted it, we had to take one of those out. So that's why we have to subtract it. But if they're mutually exclusive, meaning if they can never happen at the same time, if there's nothing in common, there's nothing to take out. So that would be 0. So that's why we have this shortcut. Again, these are on your formula sheet, so you don't have to memorize them. We're going to do an example so you can see why or how it works. The main thing here you should think about is and is multiplying, or is adding. That's the main thing you have to not even memorize. It's on our formula sheet. But if you just don't want to look at your formula sheet, that's the main thing. And is multiplying, or is adding. Let's do an example. So let's let AA be the event that a randomly selected IRSC student is an Associates of Arts student. So probability of AA is 0.34. And let's let PM be the event that a randomly selected IRSC student is on the pre-med track. So the probability that they're on a pre-med track, probability of PM, is 0.31. Finally, the probability that the IRSC student is a is AA, so Associates of Arts degree seeker, and on the pre-med track is 0.15. So I could write that out as probability of AA and PM, pre-med, is 0.15. That way I have everything that I need. I need this, and I have that. That's everything they give us. Use the information to calculate the following. Round 3 decimal places as needed, blah, blah, blah. So what is the probability that a randomly selected IRSC student is an AA degree seeker or, remember or is like this little U, on the pre-med track? So we're trying to find the probability of AA or pre-med. We have this formula up here. So the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So minus both. So let's just plug it into the formula. So instead of A, we're going to do AA, and instead of B, we're going to do PM. So it's the probability of our AA, or, so we're going to add the probability of the pre-med minus the probability that they're in both, AA and PM. Because again, remember, so if I survey everyone in here and say how many of you are degree seekers, survey you again and say how many of you are pre-med, and if I were to have either or, I would have counted you twice if you're AA and pre-med. So because I counted you twice, I had to take out one of those countings so that we only count you once. Does that make sense? That kind of thinking about it now more in like a real setting. If it doesn't make sense, just follow the formula, but just saying. So probability of AA, 0.34, plus probability of pre-med, 0.31, minus the probability of both, which they gave us, 0.15. So 0.34 plus 0.31 minus 0.15, and we get 0.5. Done. So again, taking the problem, taking out the stuff they give us, using what they give us to plug it into the formula, which they also give us. So everything's given, it's just a matter of putting it all in the right spot and like decoding it. How could I help you with this one? I want to make this as easy as possible. How could I help explain it, or what part you're not getting?
Upward U is or, the in is and.
Yep. So the union, the cup is or, and then the other way down is and. The intersection of the and. But on the formula sheet, you really don't even have to know that because they give it to you with words. So if that part confuses you, don't worry about it. Just use and or. All right, so let's do number 6. So just knocking out more examples. Use the given information to determine the probabilities below. Round solution to 3 decimal places as needed. It tells us the probability of A is 0.05, B is 0.18, and probability of B given A is 0.11. So if A and B are assumed to be dependent events, what's the probability of A and B? Let's look at that formula sheet. A and B, and it says dependent. So A and B for dependent events. Here's our formula. Probability of A times the probability of B given A. Boom. Probability of A times the probability of B given A. From the formula sheet, I didn't have to know anything. I just found which one was labeled as dependent and. So probability of A, they give us 0.05 times B given A, 0.11. Plug that into my calculator. .05 times 0.11, and we get 0.0055. That 5 is going to round up to a 6. So 0.006. Next one, if A and B are assumed to be independent. So probability of A and B, so we know we're going to look at these two. And then it says independent. So now looking at the independent. So probability of A times the probability of B. Probability of A times the probability of B. Probability of A is 0.05 times probability of B is 0.18. Putting this into our calculators. And we get 0.009. Done. Next one, if A and B are assumed to be dependent and mutually non-exclusive. Now I have the probability of A or B. So going to my formula sheet, let's look at A or B. All right, so these are my two probabilities of A or B. What did it say? Dependent. So dependent and mutually non-exclusive. So mutually non-exclusive is going to be this first one. Probability of A plus B minus probability of A and B. So I just looked to say, okay, we're looking for or, mutually non-exclusive. So probability of A plus the probability of B minus the probability of A and B. All right, probability of A, 0.05. Minus probability of B, 0.18. Minus the probability of A and B. We just found those up here. But which one was dependent? This first one. So our answer was 0.006. So in our calculators, 0.05 plus 0.18 minus 0.006. So minus whatever they had in common and counted twice. 0.224. Can I say one thing? Because this is something, you know, okay, so I go through and I do every homework problem too, by the way. So this is what I got, and I messed up, and I was like, what am I doing wrong? So I hope that you learn from my mistakes. I wanted to throw my computer, but I obviously can't because my life is on that computer. But anyways, so, and I figured out what was wrong. So I hope that this saves you. Okay, so do you see how we did this one, right? But what is our main rule? Don't round your answer until the very end, right? We rounded this answer.
Oh no.
Yes, so it's going to mess it up. I thought that, you know, like on like my lab math, those of you guys who do that before, like it kind of gives you a little bit of wiggle room. Like it says like go, you can go up with a hair because rounding, go down just a hair for rounding. This one can't. So it's free, but there are some glitches. But it's okay. So all we have to do here, this wasn't 0.66. This was up here, 0.0055. So just don't round till the very end. So 0.05 plus 0.18 minus 0.0055 equals. See, now this changes it from a 4. That 4 is now going to round up to a 5. So
You're off by like less than 1.
yeah, you're off by like what? That's tenths, hundred, by 1,000. Yeah. So don't round until your answer, until the very end. So I'm going to put a little arrow to note that. Don't round that number. That's what I got whenever I put this up here. 0.05 times 0.11. So hopefully my stress and my stuff will save you from being stressed. Because I was like, I know I'm doing this right. What's wrong? What's wrong? That's what it was. I even wrote a note on here. Don't do that. And then but I'm glad we talked about it now. All right, so last one for this example. If A and B are assumed to be dependent and mutually exclusive. So we're looking at A or B. So go into our formula sheet, A or B, and we said mutually exclusive. Oops, sorry. These two are A or B. Mutually exclusive is this bottom one. So probability of A plus probability of B. So A is 0.05 plus 0.18. And we get 0.23. Done. I'm going to say here this is from I'm going to draw another arrow from first part, I guess. I don't know. So we got that answer from up here is what I want to make sure that you realize. All right, how can I help you with this one? Same one that you're going to practice on your homework. So again, just reiterating, we're doing this together. You're going to try this one by yourself on your homework. The whole point of that is to make sure that you don't have any questions. Then you're going to practice it all. Practice taking the test as the quiz. So the quiz is kind of like your practice test. Then you're going to review and put it all together on the extra credit review. Then we're going to take the test. So hopefully by the time you get to take the test, we've done the problems together. You've done them by yourself. You had your chance to ask any questions, and you practice it. I just want to make sure that you realize why we're taking the note, why we are taking the notes, why you're doing the homework. So that way you kind of can, maybe it'll help you. Are we done on this one? All right, let's keep going. A random sample of 147 students were asked if they lived on campus or off. So again, another contingency table, two-way classification. So I have on campus, off campus, male, and female. So let's go ahead like we did last time and kind of like write it all out. So let's see how many male students were asked. So let's go across. So male, 29 plus 53 will give us 82 males. How many females? So going across, so just looking at our female row. So 52 and 13 will give us 65 females. And they tell us total, it should be 147. So let's make sure 82 plus 65. Yep, 147 is our total. Now let's see how many are off campus. So just looking at off campus, 29 and 52. So 29 plus 52. So 81 people live off campus. I'm sorry, on campus. Thank you. On campus. Now, how many people live off campus? So just looking at off campus, 53 plus 13, 66 live off campus. So let's make sure this adds up. 81 plus 66 gives us 147 total. All right, that just takes 2 seconds, and now we have everything that we need. Bless you.
One question.
Yes, please.
How do we determine if these are dependent or independent? Doesn't say.
We're going to see. Remember, always assume they're dependent. But we're going to do it. So, probability of female. So how many females, I'm just looking at females, how many females were there total?
65.
65. Is that door keep on doing that? Like, that's kind of scary. 65 females. It's weird. This place is weird at night. Scary at night. Out of how many total?
147.
147. I'm just writing these little notes. If you don't need it, that's fine. Just so that whenever you go home, you see where we got those numbers. So we said round of 3 decimal places. So 0.442. All right, so again, let's think about this now that it's organized. We don't really have to use the formula. Let's just think about this. How many are female and off campus? So looking at this, what section is female and off campus?
13.
13 out of how many total?
147.
147. So this is female and off campus out of total. So 13 out of 147. 0.0884, so just 0.088. Same thing, male and on campus. So looking at our males, how many males are on campus? 29 out of how many total? 147. So male and on campus out of our total. 29 out of 147. Oh, sorry. There we go. 0.1972, so it's going to say 0.197. Now we get to the or. So, off campus or male. So, looking at this, how many are off campus, let's say? So just looking at
65.
66 off campus?
60. 66.
Total?
Yeah, total off campus.
66.
Yeah, 66. Plus, how many are males? Because remember, or means like putting everything combined. So how many are males total?
82.
82. But do you see on this 66, we did 53 plus 13. And then looking at the males, we did 29 plus 53. So we added that 53 twice. Do you see that now? Like now that you kind of can see it. We did off campus. We did 53 plus 13. And then when we looked at males, we did 29 plus 53. So we counted that 53 twice. So because we counted it twice, I need to take one of them off. So taking out 53 out of our total, 147. So this is total. And up here we could say maybe like off plus male. So off total plus male total minus off and male. However you want to say it for your notes of how we got those numbers. Off, male, off, and male. Maybe that's better. All right, so up top, 66 plus 82 minus 53. 95 out of our 147 total. 0.6462, so it's going to say 0.64. So the or is the one that you have to be careful about double adding and take off whatever they have in common. So off campus or female. So same thing. So how many are female total? 65. Plus how many are off campus total? 66. So notice whenever you did this female, you did 52 plus 13 to get our 65. Whenever you did off campus, you did 53 plus 13, so that 13 was added twice. So minus female and off 13 out of our 147 total.
So this chart, we don't really need to look at the formula sheet. We just need to do it.
Right. The chart organizes it for us so that way we don't have to use the crazy formulas. If you want to use the formulas, you're more than welcome to. It'll still give you the right answer, but it gets a little bit more clunky. If that makes sense. Like a little, it's easier just to do it this way. So 65 plus 66 minus 13. And we get 118 out of our 147 total. Oops. We get 0.8027, which is going to round up to 3. How can I help you on this one? I hope, is it getting better now that more?
That one was much easier.
The more we do, hopefully the easier it'll be. It's just new. And that's, I think, the worst part about stats. The reading, because it's all like word problems, so the reading part and taking out what you need. And then it's just so weird. You know, where algebra is kind of like stuff that you've been doing. This is totally different. All right, so if we're good on this page, let's keep going to page 7. Last page, kind of. This one. No, sorry, not last page. Almost last page. Dang, I got a little excited. My bad. We're getting close, though. Remember, like I said before, it's like one more page, and then you finally get to the end. Yes, ma'am. Yes, please.
The one before.
Okay.
So you know how you did off-campus or mail?
Uh-huh.
So why did you do like down and then for the off-campus or female you did across?
What do you mean? The way I wrote it?
No, like the way you solved it.
Oh, gotcha.
Like when you did off-campus
Oh, right.
or mail, you did 53 and 13, and then when you did off-campus or female,
Why I switched those two?
you did 50.
It doesn't matter the order because we're adding. So if I did off-campus plus male, or if I did male plus off, we're adding. So those don't matter. So like here, you're right. I should have did off plus female. Is that what you're saying?
Like 66.
Don't think about it as horizontal and vertically because it's not going to be like that always.
Oh, okay.
So don't. That's just the way that this is set up. So don't. I like how you're trying to find the pattern, and that's good because that's like what math is. But don't think about it as that. See these. But I do see your point. Like this is bothering me because it's twice. But so like here, it's really like the first one was off campus, and the second word is female. So we really should have did off campus, which is 66 plus female, which is 65. But it was adding, so that's why it didn't really matter. But that way you could say, okay, the first one, which is off, plus the second thing, which in this one's male, this one's female, and then minus what they had in common.
Okay.
Is that better now? And then now it should work like what you're saying, like
Yeah,
vertically
I
and
just
then
like to look
horizontally.
like when I get lost, I looked at the one before, but
Yeah.
you did it like kind of different, so I was like, well,
yeah, it's the same thing. It
Yeah.
just doesn't.
it's different order.
Yeah.
Okay.
Thank you for asking that though. So yeah, so you do off plus this one's male, this one's female, and then minus both. So now they should be exactly the same. Thank you for bringing that up. I like it to be consistent. I don't know why I flipped that. So thank you for bringing that up. What else? And I'm glad you brought up the vertically and horizontally because I thought about it the first time I was learning this too. I remember like thinking that, but it's totally like not always going to be like that. It's just a matter of what the question is because they could ask you like any of these 4 options. All right. Thank you again. All right, let's keep rolling. So this one is the same concept, but it had 3. So I thought maybe this was a little bit different. So let's try this one. So a random sample of 450 students and professors were asked about their political party affiliation. We're not going to talk about politics in here. We're just doing the problem. The following contingency table, I almost didn't put this one in an example because I don't do politics in school. So anyways, but it was a good example. So we have student, we have professor, and then we have the different parties, independent, Republican, or Democrat. So suppose one party is randomly, or one participant is randomly selected from the group, calculate the following, round to 3 decimal places. So same exact concept, nothing's different. This time we just have 3 different options, I guess. So let's see how many students. So like let's go across. How many students are we looking at? So kind of like filling in the table like we did before. So 51 plus 93 plus 88, 232. Perfect. How many professors are we looking at? So 61 plus 99 plus 58, 218. It told us that total it should be 450, so let's make sure. So 232 plus 218 is 450, so that works. So that's our total. So now let's see how many independents, how many people were independent. So 51 plus 61, and we get 112. How many Republicans were asked? So 93 plus 99, 192. And then how many Democrats? So 88 plus 58, 146. Perfect. So again, let's make sure that this all adds up to our total. So 112 plus 192 plus 146. Yes is 450, so we just know that we have our numbers right. That's like our way of checking to make sure we have everything right. So we're going to do the same exact concept, asking probabilities based off this chart. So the probability of student and independent. So remember, always assume, going back to this thing. So it says and. So here's our and. Always assume they're dependent. So it doesn't tell me independent or dependent, so always use this one. When in doubt, use the first one. So probability of student times the probability of student, I'm sorry, of independent given student, because it was B given A. But remember, these charts make this part easier for us.
I was about to say you lost me on the formula because of how we did it before. I thought I already knew.
What? How did you do it?
I did the student and independent. So you have
Oh, yes, I'm sorry. I was just going to do, I have on my notes, I was going to do one using the formula and one not using the formula. Sorry if I didn't mention that. So let's just do one, or let's not do that. Let's just, it sounded good in theory. Let's not, yeah. Bye, do that.
I need frozen.
Oh, thank you. do the easiest. All right, so probability of student and independent. So looking, how many students, independent students are there? 51. So 51 independent students out of our total
450.
450. Yeah, way better. What was I thinking? 51 out of 450. And we get 0.113. Yes, let's get to the point. Do it the easiest way possible. Let's not be overachievers. Let's just do it. Let's do the next one. Probability of Republican and professor. So how many Republican professors are there? 99. Republican professors. Out of how many total people? 450. 99 out of 450. 0.22. All right, so now we have the or. Remember, the or is the ones where you have to add and then subtract whatever you added twice. So Democrat or professors. So how many Democrats are there total? 146. This is for Democrats. Plus how many professors are there total?
218.
218. Minus what did we add twice? The Democrat professors, so 58. Out of our total, which is still 450. So we did Democrat and we did 88 plus 58, which is the 146. And then professors, we added 58 again, so that's how we had to subtract it. So 146 plus 218 minus both Democratic professors, and we got 58. So we have 306 out of our total 450. And we get 0.68. Do you want to try one by yourself?
No.
Oh, sorry.
Sorry. Well, the next one.
I tried. You want to try it by yourself? Go ahead. Yeah, let's try. Okay, let's just talk through it. So probability of Democrat or independent. So how many Democrats are there?
146.
146. Yeah, Democrat, 146. How many independent? Let me put up here D. And how many
112.
independent? 112. And then independent. So minus how many Democrat independents do we have?
None.
None. Like these two things don't, like there's nothing that's in common. So there's nothing to subtract. So minus, you don't have to say minus anything, minus 0. And then there's no independent Democrats. You know what I mean? That doesn't make sense.
Unless you're Charlie Crist.
Out of 450. So 146 plus 112 minus 0. There's nothing in common. I put that there. Nothing in common. We didn't count anything twice, so there's nothing to take out. Out of our total, so 258. Out of our total, 450. So, is that a car? 0.573. Last one. So Republican, probability of Republican and independent. How many Republican independents do we have?
None.
None. So 0. I like that one. So let me put maybe like cannot be Republican and independent. I'm so glad we didn't do it both ways.
I was like, I'm already lost just looking at all the numbers.
I don't even know what I was thinking. Because I feel bad. It's like, here's a formula, but we're not going to use it. But it's easier to not use it, so.
So that one's mutually.
Yeah, good. So they can't happen at the same time, so let's go back. And let's bring that full circle. So they cannot happen at the same time. They cannot happen together. So mutually exclusive. I'm so glad you brought that up. So mutually exclusive. They cannot happen at the same time. Nice job, Milani. Look at you.
Hey.
Hey. All right, so questions, comments, concerns before we get to the last topic. That's the last one of these. We're going to get to the last topic, last thing. All right, so tree diagrams. We're just going to talk about this because sometimes it's helpful to use, but I don't want to spend too much time on it because I went through all of the homework and the quiz and the test and there's nothing on it. So I just instead of like doing an example, I'm just going to show you an example. So a tree diagram is a diagram to help you visualize the different outcomes. So for example, remember we talked about like the first person that we chose was dual enrollment, the second person could or could not be dual enrollment type thing. Well, what if it was something where like you want to find the probabilities of that and they didn't give it to us? So like they gave us those answers or they gave us the numbers. So for example, here's a tree diagram. For the first toss, like flipping a coin. So the first toss could be heads or tails. So here's the first toss being heads, and then your probability for that is 1/2. Here's the first toss being tails, probability of that would be 1/2. So this in red is the first toss. Blue is in the second toss. So if you got heads the first time, again you get heads or tails. So again you get 1/2 and 1/2. If you got tails the first time, you could get heads the second time, or you could get tails the first time. So you see how it could be like confusing, but now this tells you the options. Okay, head, 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 tail, tail, head, tail, tail. It's a little blurry on here, but it's hopefully it's better on your paper.
Nope.
No. Sorry, my bad. But now you can see, so probability of head, head, and then we did 1/2 times 1/2, and got a 4. Probability of head, tail, and multiply them together. Probability of tail, head. Multiply them together. So it just like helps you get your probabilities. It helps you organize it. That's what a tree diagram is. So we talked about it. Ready to move on? Questions for me?
No.
Nice to have you back. All right, Venn diagrams. We talked about Venn diagrams like very little. We talked about and or type thing. Where and is the stuff that's in the middle versus or is putting the whole thing together. Again, just a way to organize and visualize your different relationships. So the whole box is our sample space. So this whole box, this yellow circle is what's in A, B is in what's in, blue is in what's in B, in the middle is objects that are in both, so A and B. And then outside is something that would be like in the sample space, but not in A or B. So like, for example, if, I'm not very good at making examples off the fly. If you were asked your favorite subject, right? Where A was math, B was English. So like, what if someone answered science? So they wouldn't be in A, they wouldn't be in B, so they'd be like, science is still an option, so it's still in the box, but it would be like out here. It's not A or B. These are good for that, like doing intersections or for doing unions. They're also good for doing complements. So like that complement would be something that's outside. So like if it's not in A, so like when we're finding the complement of A, it's everything that's going to be in B and then everything that's out here as well. So it's good to find complements. So that's why they're useful. We're not going to use them. So let's keep going. Questions on Venn diagrams? All right, so the last thing, and again, I'm sure it's just something that you've seen before, but we're gonna bring it up to our speed, is the counting rule, factorials, combinations, and permutations. So starting off with the counting rule, and I have an example for each, straight from your homework quiz stuff. So the counting rule says multiply together the total number of outcomes that can result from each step of an experiment. So if an experiment consists of 3 steps with n, m, n, and k being the outcomes respectively, so step 1 has m outcomes, step 2 has n outcomes, step 3 has k outcomes, the total number of outcomes is multiplying all those together. So m times n times k. So let's see an example. Or before we talk about this, like for example, if you go to a restaurant, right, and they have like the 3-course meal, so like how many different appetizers are there? Let's say there's 3 appetizers. How many like full entrees are there? Let's say there's 5. How many desserts are there? Let's say there's 2. So how many different like options of meals can you have? So there's 3 appetizers times 5 entrees times 2 desserts. So you just multiply them all together. That's your answer. So let's do an example. So Big Julio's, right? I don't know. Julius. Oh no, I said Julio. I think it was supposed to be Julio's because I think that's one of the guys in the math department. That's awesome. I think I spelled it wrong. Anyways, so whatever. Pizza. They sell only pizza. They offer 3 different types of crust, 4 different types of cheese, 6 different meats, and 6 veggies. If you must order exactly 1 of each, how many different pizzas can you order? All right, so how many different crust options are there? 3. Times how many different cheeses? 4. How many different meats? 6. How many different veggies? 6 veggies. So our different outcomes, our different options, multiply all these together. 3 times 4 times 6 times 6. Oops. 3 times 4 times 6 times 6. So 432 different options, different pizzas. Yeah, so that's our counting rule. Questions about the counting rule? So what are the different options we have for each step? So counting rule is looking at each step. Maybe write that over here. So looking at each step. Looking at number of options for each step. Because remember, these are all going to be together on the test. It's not going to be like counting rule. Here's your example. You have to know what to use when. So next thing we have factorial. Factorial we denote, we label using, it's like the exclamation mark. So it's not like a really excited 0. It means 0 factorial. So the number of ways possible to arrange n items, which is the product. So that means multiply all the numbers from n to 1. But also know a little rule, 0 factorial is 1. So what this means is Wendy owns 5 books in this Percy Jackson series. And how many different orders can she place 5 of them on the top shelf? So how many different orders is what we're looking for here? So 5 books. So we're going to look at 5 factorial. What this means, the product of all n integers from n to 1. So that means 5 times 4 times 3 times 2 times 1. 5 times 4 times 3 times 2 times 1. And we get 120. Okay. I have an even easier thing for you. Our calculator knows factorials. So it knows, like, because what if you have 20 factorial? I don't know about you, but I don't want to do 20 times 19 times 18 times 17. Oh, I can't even say that. So let's go hit 5. So just press 5. Hit your math button right here. Scroll over to probability. And look at number 4. So math probability number 4. Press enter. So 5 factorial is 120. Let's write that out on your notes so that way you know how to find that. So factorial. So in calculator, we typed in 5, and then we hit the math button, and then we went over to probability, and then we went down to number 4, which said factorial, and press enter. And that gave us 5 factorial was 120. I don't like the way putting this 4 there. That scared me. Be confusing. So math probability, and then you'll see the factorial symbol. Questions about factorial. I like these. So like this last stuff is good. Combinations, again, did these before. So the number, or hopefully, if not, we're going to talk about like you've never seen it. So the number of ways X elements can be selected from n distinct elements where the order does not matter. Where order does not matter. So for example, if you have a bowl of ice cream and you put whatever, if you put chocolate, vanilla, and strawberry in a bowl, it doesn't matter what order you put it in, right? Versus if you put it on a cone, for some people it might matter because maybe they want one of them first and second and third. So in a bowl, it doesn't matter the order, so we would use combinations. Here's our formula for combinations. It is also on your formula sheet. Let's do this on the next page. Notice, so it's n, which is the size of the set. This is always the bigger number, by the way. And this is the number that you're going to select. So this is going to be the smaller number. So let's say out of our options, we have 10 different options of ice cream, and you're going to choose 3 of them. So it'd be 10, the way you say this is 10, choose 3. So whatever that n is, whatever that bigger number is n factorial all over n minus k factorial times k factorial. Just a crazy formula. We're going to do it one time together. I'm going to show you on your calculator. All right, so next page. Oops, over here. For real, the last page. So see, 2 more examples and we're done. So there are 19 members on a city council. At a recent city council meeting, 5 of them voted in favor of the budget increase. How many possible groups of council members could have votes in favor? So is it permutations or combinations? Well, obviously we're talking about obviously we're talking about combinations, so it's going to be a combination one. Permutations is next, but it doesn't matter the order. Either they voted yes or no. It doesn't matter what order they voted. I'm just trying to see which ones voted yes. So order doesn't matter, so it's going to be a combination. Order does not matter. Let me write it up here so that way I can use down there. Order does not matter. So it's a combination. So I'm going to do it one way, kind of like using the formula the long way. Reason being, there are some problems on the homework that want you to do like part of the formula. So I wanted to like show you the formula, and it's just pretty much plug it into your calculator. So I'm going to show you one time, but then I'm going to show you how to do combinations as a whole, because your calculator has that formula plugged in and like memorized. So there are 19 members, and we're choosing 5 of them. Remember, it's saying 19, choose 5. So we're saying, you say this, 19, choose 5. So going to our formula, here's our formula. So this would be like our n, 19 would be like our n, 5 would be like our k. So we would have 19 factorial all over the bigger number. So 19 minus 5 factorial times 5 factorial. Just plugging in 19 for n and 5 for k. So let's plug this into our calculator. So I have 19 factorial, so 19, hitting our math button, scrolling over to probability, going down to number 4, so 19 factorial divided by. Now, see how this whole thing is in the bottom? I need to put parentheses to show the calculator that all of this stuff is in the bottom. So I need a parentheses for the whole bottom, and then I need a parentheses for the 19 minus 5, math, scrolling over to probability, down to number 4 factorial, and then 5, again, factorial. So math over to probability, down to number 4. And then closing the parentheses that say, okay, all of this stuff is on the bottom, equals that. 11,628. Okay, so we did it one time in our calculator. Questions for me on this part? Because like they might say like on the homework, for example, it might say 19 minus 5 factorial like this, and that will be like the only part you have to do. So we're kind of like hitting 2 birds with 1 stone and just doing this part together. But your calculator has this combinations formula memorized. So if you want to do combinations in your calculator, I said that kind of weird. Sorry. So combination in our calculator. So I want to type in first the 19. So I'm going to try to hit for both, for every type of calculator. This is how you do it. So type in 19 first, and then we're going to go to math, scroll over to probability, and then notice number 3 says NCR. They can use R, they could use K, like it doesn't really matter, it's still combinations. NCR. So notice like the N, like this 19 is like a little subscript. Same thing with the 5, they're like little numbers at the bottom. So press enter. And then like for the 83s, like mine, see how it makes it a subscript? For the 83s, it doesn't make it a subscript, but it still does the same thing. And then now type 5, press enter. Boom, there's your answer. Super cool, right? So you don't have to worry about knowing that formula. It'll be on the formula sheet, but who cares? Just let your calculator do it. So there are going to be 11,628 possible groups of 5 city council members who voted in favor for the budget increase. Last thing, and we'll be done. So the last thing is talking about permutations. So it's the number of ways X elements can be selected from n distinct elements where order does matter. So same exact thing, nothing's different, but this time order does matter. We have a formula, it's very similar to the last one. N factorial all over n minus k factorial. Again, the bigger number goes first, the size of the set. And then whatever number is selected goes second. So for example, the total of 19 horses compete in the horse race. I don't know what happened here. This is supposed to be how many different ways can the top 5 positions be arranged. Order matters because we want to see who wins first, who wins second, who wins third. So order matters. So because order matters, we're going to use permutations. There's 19 horses and we're choosing 5 of them. So there's 19 total. Out of those 19, we're choosing 5 of them. Plugging it into our little formula up here, we have n, which is the number of the entire set. So 19 factorial all over 19 minus 5 factorial. I can plug this into my calculator. 19 math. I didn't even notice it was the same numbers. Math. Going over to probability, down to our factorial. Press enter. So 19 factorial divided by, in parentheses, 19 minus 5. Math over to probability, down to factorial. And we get that crazy thing. 1, 3, 1,95360. So 1,395,360.
Or you can choose your.
Or we can just use a calculator. Or, so let's do in our calculator, permutations in our calculator. We're going to put in that 19 first again, and then go to our math button. So 19, hitting our math button, going over to probability. Notice number 2, the second one down, says NPR, which is our permutations. Press enter. And then it gives that for us, and we're going to choose 5 of them.
You can push the button 2 first.
Yes, okay, so, like push the permutation button first. Yeah, so if you have an 84, that's a problem. So if you have an 84, you can just do math